Okay, we are going to be covering section 1.2 today of week 1. So again, week 1 is matrices and matrix arithmetic. Section 1.2 is specifically matrix arithmetic. So this slide is kind of all the encompassing ideas of section 1.2, which is about stuff we're going to do to the matrix. So there's 3 different types of operations you're going to be doing to matrices in this class, which is adding and subtracting them. That's probably adding and subtracting them in scalar multiplication are the more simple ideas. I feel like they're very intuitive. So again, we're dealing with matrices and not scalars. So by scalar, I mean just like numbers, like real numbers, like 5, 10, 12. Here, since we're dealing with matrices, which are instead matrix values, we need to redefine a little bit of these operations that we've used for scalars. So for addition and subtraction, very straightforward. Biggest things is that 2 matrices, to add or subtract them, they must be the same size, which makes sense because you add and subtract matrices how you think you would add and subtract matrices, which is just entry-wise. So if I had the matrix A and a matrix B, I look at the same corresponding entries, I add them together, and then I will form a resultant matrix of the same size with those every single entry added together. So they must be the same size matrix. It's distributive property and it's also commutative. So the order does not matter when you're doing matrix addition. Obviously, inherently subtraction is an ordered, like A minus B, probably not the same as B minus A, but like addition itself is not commutative matrix addition. Scalar multiplication is also what it sounds like. So we distribute a scalar into every entrance of the matrix. So if I had some matrix A and I wanted to multiply it by some scalar C, I just take every single entry in A and I multiply it by that scalar and I get my result in matrix B. Matrix multiplication is where things get gross. I personally hate matrix multiplication, but it is unfortunately something you're not going to be able to bypass in this class. Like, you're going to have to be able to do matrix multiplication. And I really recommend nailing that down because you're going to be taking a Friday quiz and you have to you have to multiply 2 matrices for so many different reasons. And you have a timed quiz where you want to be able to dedicate your extra time to like thinking about the problems, not doing the matrix multiplication. Because for me personally, if I was given a quiz and they're like, compute these 2 matrices, I would have to think about it. You want to be able to not have to think about it. You want to be able to just do it. But let's discuss the properties of matrix multiplication. So we are talking about multiplying, let's say A times B. So A times B is only defined when we have this property. So zooming in a bit. If A is an M by K, so M rows, K columns, and B is a K by N, so K rows, N columns. AB, the product, is an M by N matrix. So let's say A is an M by K, and B is a K by N. The result, AB, is an M by N because we take the number of rows in the first matrix and the number of columns in the second matrix, and then that defines the size of the new matrix. Second important note is that these K's must be the same number. The number of columns in the first matrix must equal the number of rows in the second matrix. It just has to be. If it doesn't, it's not defined. If these are not the same, I would say this is Q where K is not equal to Q. AB does not exist. So you just have to have that the number of columns in the first matrix equals the number of rows in the second matrix. That follows this third point that it's not commutative. So the order of matrix multiplication does matter, unlike multiplication of scalars, right? When you multiply 2 numbers, the order doesn't matter. Matrix multiplication, it matters a lot. Even so, let's say we had A and B where they're both N by N matrices. That means that AB exists and BA exists, because if we switch the order, that inner number is still going to be the same and they're going to be equal for each other, but that doesn't mean that these are the same matrix. They're probably a different matrix. So when you're doing matrix multiplication, the order that you do it in matters a lot. It's also associative, so multiplying by, that's associative means, right? We multiply by the identity matrix That's the same thing. It acts as if, like, the identity matrix, which you denote as IA, where A is equal to that, is equal to AI. Same thing as the associative property with scalars. Okay, so we just like discussed it. Let's do it. Okay, so given the following matrices, determine if each of the following matrix properties exist, and if so, find their product. All right, so we're asked to define all of the combinations. We have 3 matrices, and we have A, B, A, C, B, A, B, C, C, A, C, B. Let's first figure out which ones exist. So I've got A, B, let's do them. A, C, B, A, B, C, C, A, C, B. Okay, so A is 3, 1, 4, 0, 8, 1, which is a 2x3 matrix. B is a 1, 4, 0, 3, 2, 6, which is also a 2x3 matrix. If I try to put these two things together in this order, A, B, I need to look at these two terms. I see they are not equal. Therefore, AB does not exist. And we don't even have to think about it further. That's all we need to think about for AB. Okay, now let's think about AC. Again, we have A. I'm just gonna move over here. Let's define these. So AC is, I'm going to try to use this 2x3 matrix, and then I have C, which is 3, 1, 4, 2, 0, 1, which is a 3x2 matrix. I compare the inner numbers, 3 and 3. They are equal. That means AC does exist. So we're going to come back and solve for the AC product after we do all of these. BA, let's look at that. So BA, again, I have my B, which is a 2x3. Change this color, just so each matrix has its own color. A3 by 2. Oh wait, sorry. 2 by 3. Alright. B is a 2x3. And then I have my A. Which is, as we recall, a 2x3. Again, I compare the middle numbers. I see that 3 and 2 are not equal. So BA does not exist. Moving on, BC, so taking my B matrix, bring it down here, my C matrix, I compare the inner terms, 3 and 3, that is equal, that means BC does exist. So we will also come back and solve that. CA, C, A, E, oh shit, A. Comparing my inner numbers, 2 and 2, those are equal, so CA does exist. And lastly, CB, got my C, and I got my B. Comparing my inner numbers, 2 and 2, they are equal, so CB does exist. All right, now that we've determined which combinations do exist, we should solve for them. So the first one I'm going to do is AC. So I'm going to move these down a bit. All right. AC. Let's figure out what size AC is. AC is going to be a 2 by 2 because those are the outer numbers. So AC is a 2 by 2. We'll be doing 3, 4, 8. Actually, I'm gonna keep them their same colors. Okay, so 3, 4, 8, 1, 0, 1, A times C. 4, 2, 0, 1 comes out to be a 2 by 2. So I know AC, there's going to be 4 entries in this entire thing. It's a 2 by 2. The way that we solve for this is we do always row times column. Remember, those values are going to match. So row times column. So starting off, I have my first row. Actually, I'll use this. Okay, so my first row times my first column. So 3 times 3 plus 4 times 4 plus 8 times 0. Looking here, I took each value and then I multiplied it by its corresponding value in C. Okay, then my next value I'm going to do is my row times my column. So this is going to be my second entry in the first row in AC, which makes sense because the first row in A, so it's going to be the first row in AC. It's the second column in C, so it's going to be in the second column in C. So 3 times 1 plus 4 times 2 plus 8 times 1. Again, I have my 3, 4, 8, and then I have my 1, 2, 1. That's my first row of AC. Moving on to my second row of A. So my second row of AC is 1, 0, 1. So I have 1 times this guy. 1 times 3 plus 0 times 4 plus 1 times 0. Then I'm going to do, I'll correspond it again. 1, 0, 1, 3, 4, 0. And then my last entry is the second row, second column. So 1, 0, 1 times 1, 2, 1. 1 times 1 plus 0 times 2 plus 1 times 1. So 1, 0, 1, 1, 2, 1. That's my AC. I'm just going to simplify it by doing all the addition. So this first one is 9. Oh God. 9 plus 16 is 25. 3 plus 8 is 11. Plus 8 is 19. Yes. 3 plus 0 is 3. And then 1 plus 0 plus 1 is 2. That's my AC. AC is a 2 by 2 with these values as we defined. So that's the idea of matrix multiplication, is we just take every single row in the first matrix and we multiply it by every single column in the second matrix. We figure out what size it's going to be based on that. All right, we did AC. Let's compute our next ones. BC, we can go a little bit faster with the rest of these just because we have the idea of matrix multiplication behind us. So 1, 4, 0, 3, 2, 6, B times C. B times C is also going to be a 2 by 2 matrix because this is a 2 and this is a 2. So BC is a 2 by 2. So let's compute it as we did before. So I'm just going to write it out. So 0 times 3 plus 0, 1 times 3 plus 0 times 4 plus 2 times 0. So first row, first column. Now we've got first row times second column. Now we're going to do second row times first column. Now second row times second column. So 4 plus 3, 2 plus 6, 1. Doing it all together. 3, 3, 12 plus 12, 24, And then 4 plus 6 is 10 plus 6 is 16. So that's my BC. Similar, same idea, same size matrix, same size input matrices, result. All right, now I'm going to move this over a bit. Or maybe I'm not. Just squeeze it a bit. Okay, CA does exist. CA is going to be a 3 by 3 matrix. So this idea of when we have it like this, we're going to make the bigger version. So in these previous ones, we had a 2 by 3 and a 3 by 2 that we multiplied where the 3's went in the middle, so it became a 2 by 2. Now, if we reverse that order, like we're doing here essentially, is we're going to get a 3 by 3 instead. So we're going to make the bigger matrix. We'll do that. C, 3, 1, 4, 2, 0, 1, and then A is 3, 4, 8, 1, 0, 1. All right. So CA is a 3 by 3. Again, first row, first column. So now we only are doing 2 additions. So 3 times 3 plus 1 times 1. That's my first entry. I've got my second entry is 3 times 1 times 4 times 0. So 3 times 1, 3 times 4 plus 1 times 0. And then 3 times 1, 3 and 1 times 1 and 8. So 3 times 8 plus 1 times 1. That's our first row because we use the first row in C. 4 times 2, 4 and 2 and 3 times 1. So 4 times 3 plus 2 times 1. 4 and 2, 4 and 0. 4, 4 plus 2, 0. 4 and 2, 8 and 1. 8 plus 2, 1. Then our last row, 0 and 1, 3 and 1. 0, 3 plus 1, 1. Reuse my colors. 0 and 1, 4 and 0. 0, 4 plus 1, 0. And then 0, 1, 0, 1, 8, and 1. So 0, 8 plus 1 times 1. That's my CA. I'm going to solve for it. So 9 plus 1 is 10. 12 plus 0. 24 plus 1 is 25. 12 plus 2, 14. 16 plus 0, 16. 32 plus 2, 34. 0 plus 1, 1. 0 plus 0, 0. 0 plus 1, 1. That's my CA. Is a 3 by 3 with those values. I will write out real quick. 3, 3, 1, 4, 2, 4, 2, 4, 2, 0, 1, 0, 1, 0, 1, and then all of these. One of my biggest recommendations for when you are doing matrix multiplication on a quiz or on an exam is write this intermediate matrix. If once you feel pretty confident with it, I feel like people feel the tendency to just go straight from here to the result, but it is so easy to make an algebraic mistake here and just miss one addition, multiply something wrong, very simple stuff that's going to catapult you into getting a very wrong answer. In this class, you are doing so many things by hand that you want to maximize the amount of points you're going to get for knowing how to do those things by hand, not being docked for messing up an addition here and there and making those silly mistakes. So I really implore you to write down every single step you're taking so that if you do potentially make a mistake, which you're going to, this class has so many problems, so many things, you still get credit for the fact that you understood how to do the matrix multiplication, even if you made a small mistake somewhere. Okay, lastly, we're going to compute CB. So same idea as CA, so we're going to go hopefully a little bit quicker with that too. Okay, so C, 3, 1, 4, 2, 0, 1, and this time we got B. 4, 0, 3, 2, 6. Again, CB is going to be a 3 by 3. Okay. All right, let's do this. 3, 1 plus 1, 4. 3, 0 plus 1, 3. I need slightly more space. 3, 2 plus 1, 6. Then our second row, 4, 1 plus 2, 4. 4, 0 plus 2, 3. 4, 2 plus 2, 6. 0, 1 plus 1, 4. 0, 0 plus 1, 3. 0, 2 plus 1, 6. And then we can write out the result of that. So 3 plus 4 is 7. 0 plus 3 is 3. 6 plus 6 is 12. 4 plus 8 is 12. 0 plus 6 is 6. 6 plus 12 is 18. 0 plus 4 is 4. 0 plus 3 is 3. 0 plus 6 is 6. And that's my CB. Yay! We solved it. That's the basics of matrix multiplication. So next question is we want to compute the following matrix from the matrices above. So using what we had before. So I'm going to take my matrices, A, B, C, bring them down here, and they want us to compute ABC. A plus B times C. So first thing I want to compute is A plus B, which is very straightforward. So 3, 1, 4, 0, 8, 1 plus B, which is 1, 4, 0, 3, 2, 6. As you can see, we can add them together entry-wise. So 3 plus 1 is 4, 4 plus 0 is 4, 8 plus 2 is 10, 1 plus 4 is 5, 0 plus 3 is 3, 1 plus 6 is 7. That's my AB. Now I'm going to multiply. So now I have AB. So AB is 4, 4, 10, 5, 3, 7. That times C. So 3, 1, 4, 2, 0, 1. This is A plus B times C. Checking again. This is a 2 by 3. This is a 3 by 2. These are the same. Therefore, this is defined and it's going to be a 2 by 2. So A plus B times C is a 2 by 2. Again, note that A plus B times C is not the same as C times A plus B. A plus B, so this product C times A plus B is 3, 1, 4, 2, 0, 1, 4, 4, 10, 5, 3, 7. This is a 3 by 2. This is a 2 by 3. It still exists. These are the same. However, this is going to be a 3 by 3 instead. So if you did this instead, you would be wrong. Just understand the order that you do things matters. We usually say, like, when we're multiplying by a matrix, we have to say we're multiplying on the right or we're multiplying on the left. So like, for example, for this, I would say I'm multiplying A plus B on the right by C. If it's the other way, we're multiplying A plus B on the left by C. Okay, let's do a quick computation. 4, 3, 4, 4, 10, 0. 4, 3, 4, 4, 10, 0. Oh, I totally did the same thing twice. See, I made a mistake. You never know. I'm gonna make a lot of mistakes in these videos, I promise. 4 times 1 plus 4 times 2 plus 10 times 1. Second row. 5 times 3 plus 3 times 4 plus 7 times 0. 5 times 1 plus 3 times 2 plus 7 times 1. Doing that all out, I honestly might make a mistake here with my addition, but 12 times 16, 28. 4 plus 12 is 16. Plus 10. That's not even 12. I'm psyching myself out. 4 plus 8. 4 plus 8 is 12, plus 10 is 22. 15 plus 4, plus 15 plus 12, 27. 5 plus 6 is 11, plus 7 is 18. So you never know when you're going to make an algebraic mistake. So that is the result. It's a 2 by 2. Makes sense. Let's discuss the worksheet questions for 1.2 real quick. So this is it's very similar question, but for question 3 to what we did, but it is with less matrices. So for this one, whether A, B, or BA exists. So let's see, we have A is a 2, 0, 2, 1, 3. B is this guy. So A is a 3 by 2 and B is a 2 by 2. Determine if the products A, B, or BA exists. AB exists because these two numbers match, and AB is a 3 by 2. BA, however, if we flip it, so if we put B on the left-hand side instead, so we're multiplying by A on the left, these numbers do not match. So BA does not exist. Does not exist. I want us to compute it again. Why not do one more matrix multiplication? Okay, so we're going to compute AB because that is the one that does exist. Again, we know that it's going to be a 3 by 2, so 3 by 2. All right, row times column. Row times column. Row times second column. Now we're in the second row times the first column. Second row times the second column. Third row times the first column. Third row times the second column. Doing that out. 0 plus 4, 4. 1 plus 4, 5. 0 plus 2, 2. 2 plus 2, 4. 0 plus 6, 6. 0 plus 6, 6. That is AB, and like we said, BA does not exist. Done. If one fails to exist, explain why and calculate the ones that do. Again, BA, you can explain that number of columns in B is not the same as number of rows in A. That's your justification. Okay, question 4. Last question for the worksheet, last question for 1.2 is let M be some matrix where it looks like this. They want us to calculate M squared, M cubed, M to the 4th, and then try to discern a pattern and use what we can to predict M5 without computing it. And then what is Mn? So the arbitrary M to the any power. What does that look like? All right, so I will compute M squared out. So M squared is just M times M. Obviously, any square matrix, like any matrix times itself when it's square, is going to exist. So I've got 1, 0, 0, 1, 1, 0, 0, 0, 1. Oh, no. 1, 1. That's what it looks like. I'm going to multiply it by itself. So this is a 3 by 3. This is a 3 by 3. These match. And then the result is also going to be a 3 by 3. All right, let's do this. I would say that the most common matrix multiplication you're going to have to do in this class is 3 by 3s, so it's good practice. Okay, row times column. First row times first column. First row times second column. First row times third column. Second row times first column. Second row times second column. Second row times third column. Third row times first column. third row times third column. Okay, and when you compute this out, we get 1, 0, 0, 2, 1, 0, 3, 2, 1. That's m squared. Then to compute m cubed, you would take m squared. So cubed, you can take m squared times m. So bring this guy over here times m again. I'm just going to reveal that m cubed is 136,013,001. This is m cubed. We can continue, make m to the fourth, go to m cubed times m. Multiply it by m. And then you get m to the fourth, which is 1, 4, 10, 0, 1, 4, 0, 0, 1. So now I'm going to calculate, I'm going to predict m to the n, and then we'll do m to the fifth. So they're asking, what is m to the n for any positive integer n? So looking at this, I want to see how is the values in this matrix a product, like a result, I would say, I guess it's better, of this power that it's raised to. So here, so comparing every single entry or every single thing, where this is m to the 1, this is m to the 2, m to the 3, m to the 4. Looking at it, for our m to the n, we can see that we always have 0 above the diagonal. So 0, 0, 0. We know it's always going to stay the same. We also see that we always have 1 on the diagonal. So I can go 1, 1, 1. Now, my thing that's happening within my matrix is what's changing. So in the first thing, so I have some, the way that I want to write it is I have some function, let's define it as a function f, where f of 1 is equal to 1. Oh, and also we can note that in these spots, it's always just whatever power it's raised to. So for the arbitrary, I'm going to write n and n. Now let's talk about this last spot, the bottom left value. Here, f of 1 is 1. Here, f of 2 is 3. Here, f of 3 is 6. And f of 4 is 10. So we want to see what closed form can we use to express something that takes in 1 gets 1, takes in 2 gets 3, takes in 3 gets 6, takes in 4 gets 10. Let's think about it. So for the first one, doesn't give us too much information. For the second one, we're adding 1, but obviously it must be something more complex. The second one, it's doubled. And then the last one, it is this plus doubled plus 2. So if you think about it, I don't know, play around with it, I guess, think of things, but we can pretend like, not pretend. The answer is, if I take 1 plus 1, divide it by 2, and then multiply it by 1. So 1 plus 1 is 2 times 1. 1 plus 1 is 2 divided by 2 is 1 times 1 is itself. Here, I can take 2 plus 1 divided by 2 times 2. 2 plus 1 is 3 divided by 2 is 3 over 2 times 2 is 3. 3 plus 1 over 2 times 3. 3 plus 1 is 4 divided by 2 is 2 times 3 is 6. And then 4 plus 1 over 2 times 4. So 4 plus 1 is 5, divided by 2 is 5 over 2, times 4 is 10. So this entry here, let me expand this out. Is written as 1/2 n n plus 1. That's the closed form expression of it. So we can compute m to the 5th as well. 1, 0, 0, 5, 1, 0. So 5 plus 1 is 6. Divided by 2 is 3, times 5 is 15, and 1. And that's it. And that's everything for week 1.2. Again, the gist of 1.2 is the idea of operations with matrices. It's going to be a lot of matrix multiplication. So practice, practice, practice. That's the name of the game, to really get this down so you feel confident doing matrix multiplication in the future.